All right. Now, finally, I plan to give you a roadmap, a very simple roadmap on how to carry out hypothesis tests under certain given conditions here. Now, previously we have looked at single population mean hypothesis testing, right? Where we are trying to carry out a hypothesis test regarding the population's mean there, right? And then under this, there are a few conditions given. First of all, if the population mean is known, if the population mean is known, then um, then the types of distributions that you are supposed to use would be normal distributions, of course. Whether whether the sample size is small. If the sample size is small, we will have to make assumptions that the population distribution is normally distributed, or we have to make assumptions that the sample mean have to be normally distributed. If the sample size is greater than or equal to 30, yes, by all means, based on central limit theorem, it is stated that the sample mean distribution must be normally distributed. For the first one, for sample size that is less than 30, you have to assume that it is normally distributed, or else we don't have a predefined model for us to carry out our analysis there. Right? We could also have another conditions whereby the more realistic conditions, the population standard deviations or population variance is not given. This is the more practical case where the population standard, the variance is not given. So what should we do? The same process that we need to carry out here. We also need to assume that it is normally distributed. But because the population variance is not given, therefore we have to choose the student T distributions for our analysis instead of using the standard normal distribution Z. Right. Now, and then if you are using student T distribution, don't forget to determine the degree of freedom. Uh, that's the only difference compared to using standard normal distributions. If the sample size is greater than or equal to 30, we still have to use the student T distributions for higher accuracy analysis. But then again, if you found that the sample size is large enough, which is greater than or equal to 30, um, you have a chance to use the standard normal distributions. That value would be approximately the same as the value obtained from the student T distributions also, as long as the sample size is large enough, greater than or equal to 30 there. Okay. Now, our next sections that we're going to further discuss would be um, how do we carry out hypothesis tests for two population means, especially determine the difference between the two population means here. Now, the same idea carried out here, we would have given the population variance for both the population, and then in this case, the assumptions will still stay. If the sample size is less than 30, we still have to assume that the population is normally distributed. If the sample size is greater than 30, yes, we can use the standard normal distribution. If the variance, both the variance are not given, we will have to use the student T distributions. The conditions still stay. All right. Now I hope that is clear. And then now the calculations for uh, two population mean or two sample mean distribution in this case will be more complicated. All right. Now I'm going to show you the next part before I present to you more example. Okay, now for single population mean, for the population that the variant is known, this is the test statistics that we are using before this. So that's the formula that we use. And then the formula to calculate confidence intervals. If the variance of the population standard deviation is not known, then the test statistic that we're using is T test statistic. Confidence interval also uses the T test statistic. But for two population mean or two sample mean distribution in this case, for both the variance known, the test statistics will look something like this now. Now the test statistics will be the test statistics involve the difference between the two population mean. The formula for the standard or error, standard of margin or error in this case, which is given by this section here, is more complicated now. It's divided by square root of n, yes, but this value here itself is obtained from here. If we knew the population standard deviation or population variance for both the population, yeah, then we're going to use this formula instead. Right? Now, if the variance for the population was not known in this case, so we will have to stick to uh, student T distribution as usual. The formula will be a bit challenging. Looks very similar at first. The only difference is we'll have to use a pool standard deviation. This is the combinations of the sample standard deviations, making assumptions that uh, both the sample standard deviations or variance uh, were were drawn from the same uh, population mean, having the same standard deviation of variance. So for this last case here, we are making assumptions that the standard deviations or the variance for the populations um, standard deviations for both the populations are equal. So we make assumptions that the variance for both the populations are equal. Therefore, we are going to use the pool variance formula here. So this part represents the pool variance or pool standard deviation. This is the pool standard deviation, and then this part is the standard errors that we're going to use in the calculations of our test statistics. So the pool variance or pool standard deviation is given by here, making assumptions that both the sample mean drawn have the same uh, population variance, which means both of the sample means was drawn from the two populations having the same variance here or equal variance. That's our assumptions, man. Right? Now I hope that give you uh, an area view of what you expect to get in our next section. So in our next sections, we will look at all the example in both two population mean hypothesis testing. Right. So I hope this helped. All right, welcome back. Now we're going to go through a bit of the theory behind hypothesis testing for two populations now, and its estimation. Right? Now, the motivations behind the introductions to this hypothesis testing of two populations here. Now, this is just my example here. I'm asking that I think most of the Malaysians would actually have this question in mind. Is there any difference between the average properties prices in Selangor area and in Kuala Lumpur, right? Now, in this case, you may wanted to perform a sampling and then after that carry out your hypothesis testing to determine whether the average property price between the houses that is located in Selangor and in Kuala Lumpur, are there difference in prices, right? So you want to test the hypothesis that the average price of houses in Selangor is different from that in Kuala Lumpur. So that is one way to test and to verify whether the prices are different. The second way is we can construct confidence interval uh, to determine whether there's any difference in the property prices also. So there are two methods that we're using to determine or to make inferences in this case, right? Now, just to recap, for instance, if we label the property price, the average property price in Selangor as mu1, for instance, whereby the average property price in Kuala Lumpur is mu2, then we can set up our null hypothesis to be we are interested to find out whether there's any difference or not. This is something that is unknown. It's unknown, so we have to go out there and then test it out. Now that will be our alternative hypothesis. So in this case, we want to test whether the property price is actually difference. Now the first one, we are making a null hypothesis saying that there are no difference here. Yeah. So this is one way to write the hypothesis statement that represent two populations, or you could write in, or you can write in this format. So whichever format fancy you, right? Both of them represent the same objective that we want to verify whether the average property prices between houses located in Selangor and Kuala Lumpur are different or not, right? Now that give you a brief introduction as to where this hypothesis testing for two populations came about. All right. So inferences about the difference between two population means case one. We are looking at case one that represent independent samples, and then both of these samples are drawn from two population with the non-standard deviation, sigma 1 and sigma 2 there. That's our case number one, right? So independent uh, samples basically means the sample that you drawn from these populations does not affect the chances of the second samples being drawn from the other population. So that is the simple idea of independence versus dependent samples here, right? So I just going to read that one more time. So two samples drawn from two populations are independent if the selection of one samples from one population does not affect the selection of the second population, second sample from the second population. Else, the samples would be dependent. Okay. Now, you might encounter the following situations. Even though we are looking at drawing samples from two populations with the non-standard deviations, okay, you have to make sure that the two samples are independent. Okay, and then we have already been given that standard deviations for these two populations are known. And then number three, at least one of the following two conditions, at least one of the following two conditions fulfilled. Now, if you found that both the sample size is large enough, then by all means we can use standard normal distributions. If either one or both sample size are small, then both populations from which samples are drawn must be assumed to be normally distributed, or else we will not have any um, simple tools to analyze the hypothesis testing, right? Okay, we will look at the next section shortly. Okay, now next, these are all the formulas that we are going to use to calculate the sample standard deviations and the sample mean difference in this case. So for sampling distributions or mean, the difference between the population mean is given as such, whereby the sample standard deviation is calculated with the help of the standard deviations from the population, since the standard deviations from the population are given to us as sigma 1 and sigma 2. So therefore, this is the calculations um, for the sample standard deviation, or sometimes we just call it standard or errors or margin or errors given by this. Now that is meant for performing hypothesis testing. These are the two most important formulas that we need to remember. Now next, for calculations of confidence intervals, for the difference between the two population mean, now the formula will be given as such, and then because we knew about the population's variance or standard deviations, therefore we're going to assume that the population is normally distributed, given that the sample size is large enough. Even though the sample size is not huge enough, we have to make assumptions that it is being drawn from a normally distributed population. Therefore, we'll be using standardized normal distributions here. With the help of these calculations, the standard or errors, which is given as this, as in this formula here. Right? So I hope that is clear on the properties of that we need to use to calculate uh, hypothesis testing, and then calculating confidence intervals here. Right. All right. Let's look at example number one that involve the hypothesis testing about the population mean between two populations here. Right? Let's read through. We have a 2008 survey of low and middle income household conducted by this company here. Shows that consumers aged 65 years and older had an average credit card debt of 10,235, and consumers in the 50 to 64 years age group had an average credit card debt of 9,342 at the time of the survey. This was a long time ago. It was surveyed in US year 2009. Suppose that these averages were based on random samples of 1,200 and 1,400 people for the two groups, respectively. In this case, further that they assume the population standard deviation of the two groups were given as $2,800 and then $2,500 respectively, and then let the mu1 mu2 be the respective population mean for the two groups: people aged 65 years older and people in the 50 to 60 years age group. Okay. The first question is, what is the point estimate of mean 1 minus mean 2 here? So basically, point estimate means the difference between the estimate of the population mean here. So that is basically just equal to, now the estimate for the population mean is given as such. Okay, I'm going to highlight there. This one is the sample size, and then this one will be the average for citizen age 65 and above, and then the other average depth will be um, 50 to 64. Right. So if this one represent the populations for 65 years and above, and then the other one represent 50 to 64 years old, then the point or estimate must be the same as 10 235 subtract off in 9342 in this case, right? So if you calculate this, that should yield $892 dollar if you want to put the correct currency here. 93 oh sorry 9893 893, right? So I hope that is clear at this point. Okay. Now, second question. Now construct a 97% confidence intervals for the population's difference here, uh, the mean difference between the population. Now, first of all, we will need to write down all the informations that we have been given here. Right? So we are given for x1 is 10, 2, 3, 5, whereby x2, okay, maybe x1 is here, and then n1 is given as 1200, and then we know that the population standard deviations where the information was drawn for the first sample is given as such. Is it a variance or standard deviation? Yeah, standard deviation 2800. This is for age 65 and above, so more than 65 and above. And then this one is actually between 50 to 64. So between 50 to 64 example. Right now the information's given here. This is average credit card debt. Sorry, this is average credit card debt. So the second credit card debt is 9342. Sample size drawn was 1400, and then standard deviations given is 2500. Okay. So the first steps to do will be we have already calculated the point estimate between the difference mean between the two populations. Now we need to calculate uh, the sample standard deviations for the difference between the mean, right? Or sometimes we call that the pool standard deviation. So you can actually call that pool standard deviation, or sometimes you can just call that standard of error or margin of error. And then this is calculated as such. All right. Now the formula, in this case, we have been given the population standard deviation. So the formula is given as is square root this. And then if you plug in all these numbers here, it should be 2800 square over the n1, which is 1200, plus with 2500 square with 1400, and then square root that. And then from here, you should be able to obtain, I have already pre-calculated this to speed up the process here, 104.86. Yeah, okay. So I hope that is clear. And then once we are done with this, now we are going to construct the confidence interval. So the confidence intervals formula is given by, so just to write down the confidence intervals formula, that will be the x1 plus or minus here, because the sample size is large enough and then the standard deviations are known, so we're going to use the z-score in this case, multiply by the pool standard deviation, which is given by this one here. Okay, now before we can tabulate this, we are going to obtain the critical values from the MF19 here, right? So we are looking at 97%. Okay, so 97% confidence interval. So basically, this whole thing will be 97%, and then we know that this section here must be 1.5%. This part must be 1.5. This part must be 1.5% also. And then from the data booklet that we are getting, data booklet. All right, now from this data booklet, we are going to figure out this area here. So because we are interested in the 97% confidence interval, and then using standardized normal distributions, this whole shaded region should represent 98.5%. Okay, so by looking under the normal distributions curve, all right, now we're going to look for the area that represent 98.5%. So 98.5%, let me scroll down. 98.4 or 98.5 is 0.985. If you read that, critical value is 2.17. So this value here is negative 2.17. This one will be 2.17 there. And then that is basically our Z critical value. This is negative. This one is positive here. So I hope that is clear at this point. Once we have obtained these numbers, all we need to do is just substitute all the result that we have obtained. So this is just the point estimate, and then there will be 2.17 multiplied by the pool standard deviation. Okay, so if you calculate this, I have already pre-calculated this, you should get 665.43, and then to 1020.8 0.57 here. Okay, now that's how it look like. And then now in terms of confidence intervals, we would uh, we would conclude in such a way: we are 97% confidence that the average credit card debt would fall within these intervals, 665.43 to 1120.57 dollars. So averagely, most of the credit card debt would fall within these intervals. All right. Now I hope you guys are clear how to actually calculate the confidence intervals, and then how to actually read the informations from the MF19 there. Right. Okay. Now I'm going to move on to the next question shortly. Okay, now we have looked at one example on how to determine the confidence interval for the mean difference between two populations. And now I'm going to walk you through the same procedure that we have been using to conduct hypothesis testing. The only difference is now we are conducting hypothesis testing on the difference between the two population mean. Okay, so this is a hypothesis testing about the mean difference. Okay, now the notation for null and alternative hypothesis is highlighted below. Take for instance, if your number one, if your hypothesis testing has a null hypothesis that looks something, your null hypothesis for number one must be equal to this. Yeah, so this one will be a null hypothesis. If we're looking at option number one here, testing an alternative hypothesis that the mean of the two populations are different is equivalent to this, or you can actually write it down in this form here. All right. Now the second conditions that we might be testing for alternative hypothesis would be greater than, and then lastly, uh, it will be less than. So it's either one of the mean is less than, or the difference between the mean is less than 0. Now, the calculating test statistics, this is the most important calculations that we need. The formula to use for calculating test statistics is given here. Now, once we have calculated the test statistics, we're going to compare this observed calculations of z-score or test statistics with the critical value that we obtain from the data booklet or from your calculator. And then we're going to check whether it fall within the rejection region or not. Yeah, if it does, then we will have to reject our null hypothesis. If it does not, then we can say that we fail to reject, or we don't have sufficient evidence to support the notions to reject, right? Okay, now next I'm going to walk you through one example how we're going to carry out the hypothesis testing for difference between mean of two populations here. By using the same example like in example 1, we're going to carry out the hypothesis testing here, right? All right, example number 2 here, right? It's the same example like example number 1. The only difference is now we are interested to test at 1% significant level whether the population means for 2008 credit card debts for the two groups are different. Are they different, right? So this is what we are trying to test here, and then that is what we are going to write as a alternative hypothesis. So here I'm going to write down the hypothesis statement. So this is what we have. We have our null hypothesis would be both the mean is not different. So I can say that mu1 should be the same as mu2 in this case, whereby the one that you're interested to verify now, are they actually different? So this is something like unknown. This is what we like to assume to be correct. So this is the one that we're going to test it out shortly here. All right. And then what we need now would be the same idea here. We need the test statistics. All right. The test statistics that we are using, since the standard deviation is given, so bear in mind we have x1 is equal to 10235, n1 to be 1200, and then finally we have that standard deviations for the population is given as 1200, that's given. And then for the second one we have 9342, n2 to be 1400, and then the standard deviations for the population is given as 2500. Is it 2500? The standard deviations for this, okay, hold on. I think I wrote down wrongly. This standard deviation is supposed to be 2800. Okay, so those are the informations that we are given. And then we know that the standard deviations are given. Therefore, we're going to use the z-score in this case. So the calculated or the observed z value here will be given by this one here. So the mean difference divided by this value here, the standard of errors or margin of errors. Now we have calculated margin of errors from our first question just now. That actually give us 104.86 previously. So from here we're going to calculate our test statistics. This is our point estimate. Our point estimate is 893. Subtract off the difference between these is actually 0, and then divided by 104.86 here. And then if you try to use your calculator there, you should use 8.52. I have already pre-calculated this, right? Okay, now once you are happy with your test statistics result, we're going to go back to the theoretical numbers that we can get from the data booklet. Right. Now we are interested with 1% significant level. So our alpha is 1%. This is the type 1 errors here. So 1% means this region, rejection region, would consist of 0.5% on this tail and then 0.5 on the other tail. Now you need to check your hypothesis testing statement whether we are referring to whether we are referring to the a single tail test or two tail test, because the statement has one not equal sign, so it must be a two tail test in this case. So both n represent 0.5%, and then by reading this from the data booklet, we will need this area here, which will be 99.5%. All right, now that's the one that we're going to read from the data booklet itself, 99.5%. So you can see that 99.5, 99.5, where is it? 99.5 is around here. Now you have two options here. Either you can choose this one, or you can choose this one. Doesn't matter which one you choose, either this one or this one. Right. Now, take for instance, in this case, I'm going to choose 0.9951, for instance. Therefore, from my data booklet, I will write down my critical value as negative 2.58. This one will be 2.58. Now, I'm going to compare my test statistics with my critical value. And then from here, I found that, so the analysis part, I found that my test statistics 8.52 is around here. So 8.52 is somewhere here. So this is 8.52. Now these test statistics actually fall within the rejection region. So this is larger than the critical value. Therefore, our conclusions will be we will have to reject our null hypothesis. Once you reject the null hypothesis, then indirectly we are saying that the alternative hypothesis would be true. Uh, so by saying that the average credit cards depth between the two groups is not difference. Sorry, uh, are not difference. Sorry, right? So therefore, the conclusion here, I'll write down a conclusion. Therefore, we can say that by rejecting the average credit card debt between the two groups are not different. Okay, so I hope that will be useful for your learning. I will see you guys again. All right, let's look at an example that is relevant to case number 2 here. Right? Okay, now let's read through the question first. A consumer agency wanted to estimate the difference in the mean amounts of caffeine in two brands of coffee. Now, the agency took a sample of 15 1-pound jars of brand 1 coffee that shows the mean amount of caffeine in these jars to be 80 milligram per jar, with a standard deviations of 5 milligrams. Another sample of 12 1-pound jars of brand 2 coffee gave a mean amount of caffeine equal to 77 milligram per jar with a standard deviations of 6 milligrams. Now we need to construct the 95% confidence intervals for the difference between the mean amount of caffeine in 1-pound jars of these two brands of coffee. So in this case, we can make assumptions that both the population are normally distributed, and then standard deviations for these two populations are equal, but is unknown. Right. So we're going to write down all the informations given for us. For brain 1 coffee, okay, we have what do we have here? Sample of 15, N1 15, and then the amount of caffeine, the average amount of caffeine is 80 milligram, and then its standard deviations for this sample is given by 5 milligram there. Now for brain number 2, we have a size of sample size of 12. This is 1, this is 2 here. It has an average of 80. Is it 80? Let me see. Equal to, sorry, 77. 77 milligram. And then the standard deviations of 6 milligram. All right. Now these are the informations given to us. So first thing first, we are going to construct a confidence intervals for the difference between the mean amount of caffeine in 1 pound jars of these two brands of coffee there. Right? So from here, since we are not given the population standard deviation, we can assume that both the population having the same standard deviation. Therefore, we have to calculate the pool standard deviations first. Right. Now that will be SP given by N1 Alright, now if you're unsure about the formula, do refer to the data booklet there, right? So from here, all you need to do is just substitute all this value into here, and then I have already pre-calculated this. It should end up with 5.4626, right? Up to you. You want to leave it as a 5.463, that is fine. Okay, now that will be our pool standard deviations. And then once we have obtained this, we are going to calculate the margin of error, which is given by this. Okay, now this is given by the pool standard deviations divided by its sample size. Okay, so from here, we will get 5.4626 multiplied by 15 plus 1 over 12 here. And then eventually you will end up with, based on the one that I have pre-calculated, is 2.1157 here. Right now, that will be our margin of error at this point of time. And then once we are done with this, the next thing we are going to work out is the confidence intervals, the 95% confidence interval. I'm going to write down the formula first. The formula will be this. Oops. I shouldn't be using a standard normal distributions here. I should be using T distribution because the standard deviations for both the populations are not given there. Right. So please be wary of that. So it should be T distribution and then multiply by the margin of error. Alright. Now all I need to do now is to find out what is the critical value that represent 95% confidence intervals. So for 95% confidence intervals, I should be reading this area here. So this area would be 97.5%. 97.5%, and then the critical value is given here. All right. So for that, I'm going to go to this data booklet. Under T distributions, I'm supposed to look for 97.5%. On top of that, don't forget, because we are using student T distributions, we have to work out the degree of freedom here. So the degree of freedom is given by n1 plus n2 minus a 2. That is basically 27, 25 here. Degree of freedom equal to 25. So all I need to do now is go on to the data booklet, look under 97.5 column, and then look for degree of freedom equal to um, 25. So 25 would be somewhere here. All right, 25 would be somewhere here. All right. Now that will be my um, 25 will be somewhere here. That will be my 2.06. So my critical value here will be 2.06, negative 2.06, 2.06. Now, once I have obtained the critical value, all I need to do now is to substitute all the value that I have. Here, I'm going to write that down. That will be 80 minus of 77, plus or minus here, and the critical value 2.06, and then standard deviations, the margin of error is 2.1157. Okay, and then once you calculated this, you will end up, I have already pre-calculated this, negative 1.36 to 7.36 milligram. So I'll write down the unit at the side here, milligram. Okay, now I hope that is clear how we are going to use a pool standard deviations to calculate the confidence intervals in this case. Right? I'll see you in the next question. All right, let's continue on with example number 4 now. A sample of 14 cans of brand 1 diet soda gave the mean number of calories of 23 per can with the standard deviations of 3 calories. Another sample of 16 cans of brand 2 diet soda gave the mean number of calories of 25 per can with a standard deviation of 4 calories. At the 1% significant level, can you conclude that the mean numbers of calories per can are different for these two brands of diet soda? All right. Now assume that the calories per can of the diet soda are normally distributed for each of the two brands and that the standard deviation of the two populations are equal. All right, now this is what is given to us. We're going to label all the informations given to us. For brand 1 again. So for brand 1 we have number of calories of 23 per can, a sample of 14 can. The average, and then standard deviation of 3 there. And then for brand number 2, we have 16 cans. Calorie, we have average calories of 25, and then it come with the standard deviations of 4 calories there. And then our alpha is 1%. All right, so this is what is given to us. These are the both the assumptions normally distributed, and then two populations having the same standard deviations. Okay. Now, the first step in carrying out this is we have to write down the hypothesis statement. All right. So here, can we conclude that the mean numbers of calories per can are different for those two brands of diet soda? So our hypothesis testing statement will be here. The null hypothesis must be they must be the same. Here I'm showing you a different way of writing the statement now. and then the second one, oops. So the second one is not the same. All right. Our significant level is 1%. All right. Now the next step would be to calculate the pool standard deviations. Before we do anything, it's always good to calculate the pool standard deviation. I'm going to write down at the side here. It'll be easier. So calculating the pool standard deviation, that will be N1 is a very long formula there. Okay. And then if you substitute all this value in, you should be able to obtain this to be, I have already pre-calculated for the ease of reference here. So it's 3.571 here. And then from there, we are going to calculate the margin of error, which will be given by this formula here. All right, now shouldn't be a problem. You can use all these informations that we have obtained, and then finally you will arrive to this number here, 0.67. I try to leave it as many decimal places as possible before I finalize my answer. And then lastly, my test statistic would be given by because the population standard deviations are not known, so therefore I have to use my observed t value here, which would be x1 minus x2 subtract with 0 divided by this margin of error. Okay, and then by calculating this, I should have, let me see, 23 minus 25 here divided by 1.3067, and then the final answer I have already pre-calculated is negative 1.531. Okay, and then now we are ready to compare the critical value that we can obtain from the data booklet. All right, now before that, I always forgot this. Before that, don't forget to determine the degree of freedom because we are using a student t distributions here. So degree of freedom will be equal to n1 plus n2. I'll try to write down the formula one more time. N1 plus n2 minus a 2 here. So that will be like here 30 minus 2, 28. And then next is the significant level is 1%. So therefore, right, so it's 1%. Therefore, this region that we are looking at, I'll try to label this. So this region that we are looking at would be 99.5% because each tail here comprise of 0.5%. So the total area that we need to obtain from the t distribution is 99.5%. So let's go ahead and then read the 99.5% here. Okay, so under 99.5%, our degree of freedom is 28. So under this 28, and then that would actually give me this value here. So under 28 and then under 99.5%, that will give me 2.763. So negative 2.763. This is 2.763 here. And then finally, we can analyze these two or compare these two result. We notice that from here. So this is the analysis part. We notice that the critical value, this is our critical t value. So our critical t value is much more smaller than the observed t value here. Our observed t value is somewhere here. That is negative 1.531. So here we can say that our t is greater than the critical value. So because it's greater than the critical value, we know that these are all rejection zone. Okay, so therefore, we would fail to reject our null hypothesis. Okay, now knowing that we fail to reject our null hypothesis, therefore um, we can conclude that there is no difference in the mean numbers of calories between these two brain 1 and brain 2. Now that will be how we carry out the hypothesis testing for the mean difference between two populations where its standard deviations are not given. Right? Now I hope that